Let me go through the four major nuclear reactions that you might encounter on an exam. Listed here: alpha decay, beta decay, electron capture, and gamma radiation. And so each of these deal with a radioactive particle, and we have a certain way of writing it to make our balancing of the nuclear reaction cleaner. Like this here is an alpha particle. This happens to be what an alpha particle is. It's a helium particle with two neutrons, which has been stripped of its electrons. Now notice that the charge doesn't show up here. If it's been stripped of its electrons, it would have a 2+ charge. The reason it's not shown here because these are nuclear reactions, and the chemistry or the process takes place in the center, not with the outer electrons, the valence electrons. So this is a helium core that's spliced out of the nucleus of a lead particle here, right? And so you have to kind of review isotopes a little bit, right? So for isotopes like this lead 212 isotope, we have, this is the total number, and down here is the number of proton. And the way we've written it helps us balance this equation, as you will see here in a second. So a beta particle is an electron, and I'm going to go over here and show you how we abbreviate these particles. So all isotopes are written as you know. Now electrons are written like this. So they're similar to isotope symbols because the top one is our total mass here, and so we know that electrons don't have any mass. And then we don't really have a negative proton, but this -1 symbol here will help us balance whether it's beta decay, which means an electron is ejected, or electron capture, which means an electron is mopped up. And we do the same for a positron, which is a positively charged particle with no mass. So it's kind of the opposite of an electron. So, but instead, we still use an E here. It's not really an electron, but we don't want to use P because P represents a proton, and a capital P is a phosphorus atom. So we can't use P here. You're already familiar with the alpha particle. Sometimes you'll see it written as the alpha, Greek alpha, but and then, you know, we're not going to see the neutron all that much, or the gamma particle, but the three I just circled are important to understand. Now, what happens during alpha decay, as I said, we have a helium particle that's spliced out. So it gets ejected and it does its radiation and its damage and whatever it does. So it's ejected. And so all we have to do is subtract the two neutrons and the two protons from the core to determine which element is produced in this process, right? So if we take 240 and we subtract 4 from it, we get 236. And 94 minus 2 equals 92. And then based on the 92, you can go to the periodic table, find the atomic number 92, and then you know it's uranium. So these numbers add up. So the top numbers here, 4 plus 236 equals what's on the left. And the same is true for the bottom, and that works beautifully for the positrons and the electrons, as we will see. So let's practice a couple, because this is fair, right? So if I ask you to write the complete balanced nuclear equation for alpha radiation of radium 226, you write the symbol radium, right? So you find radium, so it's right here. This is how you know that the number is 88. So you write 88. Then you must know that alpha radiation is this. And then all you have to do is take the 226, subtract 4. So we end up with 222. Take the 88, subtract 2. So we end up with 86. Now we got to go find 86. And that's radon. So Rn. And you are done. Let's do the same thing here. Alpha decay, this you need to know again, is our helium-4 2, and then we do what we just did again. 179 minus 4 is 175, and then 79 minus 2 is 77. And so you go find 77 on the periodic table here. And so that's the atomic number, that's our symbol, and we just write it in here, iridium. So that's alpha decay. The next process is beta decay, meaning alpha decay means a helium particle is with 2 neutrons is ejected from the core. So here also this electron comes from the core. So it really comes from a neutron. So you're taking a neutron here and you're turning it into a proton. Okay? So we write the electron like this, again, for the purpose of being able to keep track of it and balancing it. The total mass doesn't change. It's still 228, but we have increased, so we've turned a neutron into a proton, right? If you take a neutral particle and you take a negative particle out of it with no mass, you end up with a proton. You end up with a particle equal mass. Neutrons and protons have equal mass, so that's just going to go up, right? So that's another thing you can just memorize if you want. The proton number is going to go up, and so 89 minus 1 is going to be 88, so that needs to balance. So let's practice a couple, right? So beta decay, understanding that that would be E, 0 and minus 1, so for both of them, that's the particle that's ejected. And then the other symbol or isotope you need to determine is, of course, going to have an atomic number increase. So we go look at what atomic number 92. We'll go find number 92, and that's uranium. So now I can just put that in. And here we have 214, right? So 0 plus 214, that doesn't change, it stays. But I do need to add a number to the 82, so now I'll go to 83. So I'll go and find 83 on the periodic table, and that's bismuth, Bi. So that would be beta decay, decay meaning ejection, so the electron has to be on the product side. And then there's also positron emission, which that's that positively charged particle. So here we are going to see a reduction in the atomic number, and so now we have a positive particle. So this time it's ejected from one of the protons here. So one of the protons loses its positive charge and turns into a neutron. That means we have a reduction in the atomic number. Let's practice a couple of those. So here we have carbon, and that's positron emission, so 0 and plus 1. So we have 11, and then we need 5, because 5 plus 1 equals 6, right? We need 5 plus 1 to equal 6. And so we go look this up. This is going to be, oh, I don't have the periodic table, but it's boron, all right? So atomic number 5. So we put a B, and we can do the same thing for the molybdenum isotope here, right? And it's 98, and then 42 goes to 41. We go look up 41, and 41 is niobium Nb. Okay, excellent. So there's only one left, that's electron capture, and electron capture is simply the opposite of what beta decay is, right? So if we did this way, we would have a beta decay. But so now we have to have this particle on the left side, and then we do what we always do. We just add the top. 125 plus 0 equals 125, and then 53 minus 1 is 52, and then we go look up what that symbol is. Let's practice that a couple times, and then it's your turn to try the homework, right? So electron capture. Understanding that the particle, the radioactive particle, is part of the reactant side, and then just determining what this is. So, oh, I don't have a periodic table here either, but I assure you that's going to be boron. It's one less than that. The antimony I'm going to have to look up. But if you can figure out what the particle is, and you can figure out where to put it, right? Capture means on the left side. You can then generate or determine. So now we need to look for 50. So I'm going to go back to periodic table, and 50 is tin, SN. All right. this is it. Those are the 4 major processes, and but there's also half-life and some other things you need to learn, but those 4 are going to be on the exam, so it's good that you are watching this video.